Welcome to Educator, Introduction to Chemistry. What is chemistry? Chemistry is an experimental science, and chemistry is one of the most significant sciences at work today. Chemistry connects with everything in your everyday life. There's chemistry in the chair you're sitting on. There's chemistry in the food you're eating. There's chemistry in the car you drive. There's chemistry in your cell phone. Chemistry is at the heart of the materials that make all these things that you work with every day. And so chemistry is a really significant and important science. Chemistry is also an experimental science. That is to say, all the results of chemistry, all the activities that go on in chemistry depend fundamentally on chemists doing experiments. And during this course we shall see some of those experiments and discuss how the chemist interprets them and what use the chemist can make of the facts derived from those experiments. Chemistry looks at matter and its changes, and also at energy and the changes of energy that occur during various processes. Matter is pretty much everything that's about you, the kinds of things we mentioned before. The gases of the atmosphere, the water of the ocean, the solid earth, metals, plastics. All these are examples of matter in its various manifestations. And matter undergoes changes. You observe those changes every day. You see materials degrade, you see one thing change into another. And again, those are the central ideas and the central subjects of chemistry. Understanding those changes, understanding their relationships, both mathematical, quantitative, and qualitative. Those are all critical parts of chemistry. But chemistry is also interested in the energy changes that occur when matter undergoes change. And we shall explore the energy changes later on in this course, both in the realm of chemical changes and in the realm of what we call physical changes. And in a few moments we will discuss the distinction between those two. Chemistry is also a central science. What do I mean by that? Chemistry links together many other sciences in a central mode, a central vein. Let's look at that schematically. We have chemistry in the center. And other sciences with which you're familiar, physics, biology, earth sciences or geology. In every one of these other sciences, there's a powerful link to chemistry. Let's trace those links one by one. The first, chemistry to physics, involves a subdiscipline of chemistry known as physical chemistry. And in recent years, physical chemistry has also become interwoven with computational chemistry. At the most fundamental level, this link involves quantum mechanics, which is not going to be a subject we will touch on very deeply, but one that we will interact with during our course. Quantum mechanics is a very fundamental way of looking both at physics and at the fundamentals of chemistry. Now let's look at the very important interface between chemistry and biology. This is where much of the most exciting science of today is taking place. You may have encountered it in the press, in TV shows like the CSI series, various other shows like that, in terms of biochemistry and DNA and cloning and other interesting and current subjects. These all fall into two areas which are so close that there's hardly any distinction between them. One of them is biochemistry, and the other molecular biology. These two areas have been among the most successful areas in recent science, and they owe their fundamental understanding to an understanding of the chemistry that takes place in biological processes. And the final link I want to make is between chemistry and earth sciences, or geology. It's not surprising that there's a tie between chemistry and earth sciences. After all, earth sciences are largely about the things that make up the crust of the earth, that make up planets, matter, in other words. And so earth sciences are reflected in chemistry in terms of geochemistry. This is the subject that has to do with the composition of rocks, how their compositions change, and the relationship between various different types of rocks and their chemical constitution. So, just to summarize, every good physicist knows some chemistry, at least some quantum chemistry, and every good chemist knows quite a lot of physics. Every good modern molecular biologist knows biochemistry and molecular biology, and has a lot of chemistry to take along the way to getting a mastery of modern biology. And finally, every good geologist has an understanding of the chemistry that underlies his or her science, the chemistry of the rocks. So here is chemistry as a central science, pinning together several other critical sciences. Now let's talk about properties of matter. We've discussed what kind of things matter is. Matter can come in many, many different forms. Familiar to you are probably matter as a gas, for example, the atmosphere, the air. Matter in liquid form, we're all familiar with water. And matter as a solid, the kinds of things that are substantial, metals, plastics, and the like. These are all different forms of matter, and matter can be characterized. That is to say, we can specify what kinds of matter we're discussing by specifying what are called its physical properties. Here are some examples of physical properties. Mass is a physical property. Temperature. Illustrated below are the kinds of devices that chemists use to establish mass. The balance, what is shown is a very precise analytical balance to determine the mass of an object to be used in a chemical experiment, and of course the familiar thermometer to determine the temperature of an object during the course of an experiment. So we have mass, we have temperature, we have other properties, for example, extension, size. That's also a physical property, the length, the breadth, the height of an object. These are all part of its physical properties. On the other hand, there are also important chemical properties. And illustrated below, we see an example of chemical properties that will actually undergo a change during a chemical experiment. Look at these three pictures. Here we see a silvery gray metal. Let's call it magnesium. Here we see a bright yellow substance which happens to be one of the elements, as is magnesium. This is sulfur, a yellow solid. These two materials can be characterized by their physical properties. They have specific densities, they have specific colors, etc. But they can also be characterized in conjunction by their chemical properties, because if we mix this metal with the sulfur and warm them together, a vigorous change occurs, a vigorous chemical reaction. The two react, in fact, almost explosively, certainly to the point of incandescence, that is, glowing red hot. And when the subsequent material that is produced cools down, we have this rather off-gray substance, a gray solid, which is magnesium sulfide. That's an example of a chemical process and a chemical change. So a chemical change, a chemical property, is one that involves reactions. And much of chemistry is about exactly that, the chemical changes that involve chemical reactions. Now let's be a little more specific about the kinds of physical changes we may encounter in our everyday experience, how they come about, and how they can be reversed. Because the reversal is actually the key to understanding a difference between physical change on the one hand and chemical change on the other. A familiar physical change is melting. Here we see some ice that is melting to give liquid water. Ice is a solid. We'll characterize it by little s, meaning solid, and water at ordinary temperatures is a liquid, characterized by small l. Now that's a change that occurs when energy is provided to the ice so that it melts to give liquid water. That's the kind of energy change that chemistry is involved with also. And I'm sure you're familiar with the fact that this is a reversible process. This physical change, like most physical changes, is readily reversible. How would you reverse this change? Think about it for a minute. We've all done it at home constantly. We take the ice cube tray, we fill it up with water, we put it in the refrigerator, and hey presto, the liquid water goes back to ice. Another example of a physical change which is reversible easily by changing the physical circumstances. In this case, by changing the temperature of the environment around the sample of matter. We'll see that temperature changes are very critical to understanding energy changes in physical and in chemical processes also. So that's just one example of a physical change, and next on our list is another familiar physical change. Here we have liquid water, standing on the stove in an open pot to which heat energy is being provided, and we all know what happens to that. Eventually, that liquid water will boil, giving us gaseous water or steam. Since steam is a gas, we can put a little g in there indicating the gaseous state of steam. By the way, don't be confused. It's very easy to misunderstand what steam is. If you watch a kettle boiling on your stove, you may see a cloud of white, misty material appear in front of the spout of the kettle. That's not steam. That's water vapor. That's water that has been ejected from the kettle as steam, but has condensed as it hits the cool air and makes a lot of droplets. Clouds are liquid water in droplet form. Steam itself is not visible. Steam is invisible. And if you look very carefully at a kettle that's boiling, you'll see a space just in front of the spout where you can see no condensed water, where you can see no mist. In that space is the real steam. So steam is invisible, as are many gases. And this process, water being evaporated to give steam, is also a process that's easily reversible if you change the ambient conditions, the conditions around the physical change. Steam will condense to give liquid water if we cool it down. Again, that's something that's very evident and very apparent. Incidentally, this is evaporation. We might as well start using the proper technical terms. And this is condensation. Now, a very important and very widespread physical change of a different kind is the process of forming a solution. And we've illustrated that with a very homely example. Many of you probably take sugar in your coffee, and you know exactly what happens. You take a spoonful of sugar, you add it to a cup of hot coffee, you stir it, and the sugar disappears. That is, it dissolves in the hot coffee. Of course, sugar will dissolve in cold water too. Salt will dissolve in coffee. Most of us would prefer not to have salt in our coffee, but it will dissolve. The process of solution is a very common example of a physical change. And so here we have a hot water. We're adding to it some sugar, and we're making a sugar solution. We've seen above how these two processes can be reversed by changing the physical circumstances, the temperature, the surroundings, and so on. The process of solution can be reversed also, but that's a somewhat more complicated reversal. We have to take the solution and heat it and boil off the water in order to recover the sugar. But it can be recovered completely and quantitatively from the sugar solution by a simple physical process, namely boiling. If you have any experience in candy making, you may know something about boiling sugar solutions to recover the sugar. Only in candy making, you also initiate some chemical changes when you heat the sugar too hot and you begin to caramelize it to make it brown. So here, in summary, we have three common kinds of physical processes, each characterized by a change of state of some kind, a change of nature. Here, a solid going to liquid, here a liquid going to a gas, and here a liquid going to a solution. Each of them reversible by simple physical processes. Chemical changes are something else again. Chemical changes cannot be reversed by simple physical processes in general. I don't want to make too many wide-sweeping statements because you'll probably look in your books and find an example that will contradict me. But in general, chemical changes can be reversed, but it's a much more complicated process. Take, for example, the chemical change that we looked at just a few moments ago when we looked at a chemical reaction. We looked at magnesium, a solid, plus sulfur, the yellow solid element, going to magnesium sulfide, also a solid. Notice that for the first time I've written down what is a chemical equation. A chemical equation expresses the results of a chemical change. And just like an algebraic equation, a balanced chemical equation must have the same terms on the left-hand side as on the right-hand side. 1 plus 1 equals 2, A plus B equals X, Mg plus S equals Mgs. Notice, the same terms, 1mg and 1s, come into this equation on both sides. We'll get much more into a dissection of what that means, both in terms of chemistry and also in terms of the quantitative aspects, the mass aspects of chemical equations later on. But for the moment, let's just take this as our first example of a chemical change. Now, I told you that reversing a chemical change can be a complicated process. Let me illustrate what that means by actually carrying out a reversal of this chemical change. I want to get MgS back to Mg plus S. I cannot do it as I did the reversal of a physical change simply by heating the MgS or cooling the MgS or trying in some way to divide it. I have to do quite a bit of chemistry to get the Mg and the S back to MgS, and in the process I'm also going to be doing some other chemistry which is also not easily reversible. Let me illustrate this and show you what I mean. We take our MgS and we heat it in oxygen. This is not an equation, this is just a chemical pathway, hence the arrow rather than the equals sign. And under those conditions, we make another compound of magnesium, that is magnesium oxide, and a gas, SO2, sulfur dioxide. We carry out this change because it turns out we do know ways in which we can make magnesium from magnesium oxide and sulfur from sulfur dioxide, but that also requires some complicated chemistry. Magnesium oxide, when heated to very high temperature with elementary carbon, that is charcoal, generates magnesium and the gas carbon monoxide. So we've come halfway. We've got our magnesium back, but we still have not got our sulfur back. And that too is going to require some complicated chemistry. Again, we can use carbon as the reagent to carry out that process. And again, we produce carbon monoxide and sulfur. So we've recovered our Mg and our S, but in the course of that, we've consumed carbon and we've made carbon monoxide. Just reinforcing the fact that chemical changes can, in general, be reversed, but the reversal of a chemical change is a much more complicated process than the reversal of a physical change. And in fact, that's one way in which we distinguish between physical changes and chemical changes. Physical changes can generally be reversed by changing some simple things like temperature, pressure sometimes, related matters. Chemical changes can be reversed, but only in general by doing more chemistry. Most of the matter we encounter in everyday life comes as a mixture. And mixtures can be of two types, heterogeneous and homogeneous. Let's talk first about heterogeneous mixtures, and I've decided to illustrate that example with a very familiar substance, even though you may never have seen it in this form. This is a photomicrograph, an enlarged photograph of milk. Now it's interesting that if you go to the supermarket and look at the milk cartons on the shelves, you will usually see the milk described as homogenized milk. In scientific terms, that's just a misnomer. Milk is not a homogeneous substance. As you can see when you look at it under the microscope, milk consists of two quite different materials. It consists, in fact, of a suspension of fat globules, the fat that can be concentrated into cream or into butter from milk, suspended in a watery solution which contains dissolved in it sugars and proteins. So milk is a heterogeneous substance. Another very familiar heterogeneous substance, which you can look at carefully when you go out into the garden and pick up a handful of dirt, is of course dirt. Dirt is heterogeneous, and depending on where you pick it up, it may have different materials in it, different makeup, but normally dirt has some organic matter, decaying vegetation, pieces of wood, etc. Some inorganic matter, usually some sand, some silica, and maybe other substances. Now, all heterogeneous substances can be separated, in principle at least, into homogeneous mixtures, homogeneous substances. And homogeneous substances have the same properties throughout. This contrasts with the heterogeneous substances which have different properties from part to part. Some familiar homogeneous substances include such common things as air. We're all familiar with air, and air has the same properties throughout. Gasoline, again, if you look at a sample of gasoline, as you pump some into your car or you get some for the lawnmower, it's a clear liquid, sometimes colored. It has the same properties from part to part. And another one I'll take is vinegar. Let's be very specific. Instead of balsamic, we'll just choose white vinegar, the simple vinegar. White vinegar is a colorless liquid which has the same properties from part to part. But if you examine a homogeneous material carefully, you may be able to separate it into different pure substances. And so we can classify homogeneous materials into two classifications, one of which is solutions. Now, we've met solutions before. When we stirred our sugar into our coffee, we made a solution of sugar in coffee. We can make a solution of sugar in water. Those solutions, sugar in water, salt in water, are homogeneous, but you can vary the composition of the solution. You could put more or less sugar in your coffee. You can put more or less salt in your soup. And so a solution can have variable composition even though it is homogeneous. And that's how we can distinguish a solution. But a homogeneous material may not necessarily be a solution. It may in fact be a pure compound. Familiar examples of pure compounds that you've encountered in your everyday life are cane sugar, the stuff you put in your coffee. That's a pure compound. Its properties are constant from part to part, but they do not vary like a solution. It does not have variable composition. It has fixed composition. Similarly, salt, sodium chloride. Salt is a pure compound of fixed composition, and so is water. Water is a pure compound of fixed composition. Pure compounds can be further subdivided also into two categories: compounds and elements. Whereas a compound is made up of elements, an element cannot be simplified further. We'll define elements in a more rigorous way later on, but for the time being, let's just take it that an element cannot be further simplified. whereas compounds can be broken down into elements. So there we have the taxonomy, if you like, of materials. Let's summarize. Materials can be heterogeneous, having different properties from part to part, or homogeneous. Heterogeneous materials can be divided into their homogeneous constituents. Homogeneous materials, which have the same properties throughout, can be subdivided into solutions or into pure compounds. And solutions can have variable composition. The pure compounds come in two categories. They're either compounds, which can be broken down further, simplified further, or elements, which cannot be further simplified. Everything we know in chemistry can be encompassed in this scheme of compositions of matter. In this problem, extra example 1 for lecture 1, you're asked to classify whether certain observed changes are either chemical or physical. So let's remind ourselves what these terms imply. A chemical change means we're forming new compounds. Whereas a physical change involves a change of state. Now, a change of state can mean something going from liquid to gas, for example. Or a solid dissolving to make a solution. So with these ideas in mind, let's now look at each of these 4 changes and try and interpret them. The first is the rusting of an iron nail. Now, what do we see? We observe a new compound. That's the reddish-brown material that is formed on the surface of the nail. And that compound is an iron oxide. Therefore, this change is in agreement with our definition of a chemical change, which involves the making of a new compound. Therefore, we have here a chemical change. Let's look at the second example, the evaporation of dry ice, solid carbon dioxide. What do we observe? We observe the disappearance of solid carbon dioxide. But is anything new being created? If we were to do this, for example, by putting a small piece of dry ice inside a balloon and sealing off the balloon, we would observe that the balloon expanded, but that if we took that balloon and cooled it down again, for example, in liquid nitrogen, very cold material, we would get back dry ice. This is just a change of phase. The solid carbon dioxide is going to gaseous carbon dioxide. And that is just a change of state, solid to gas. Constantly, this is a physical change. The third of our examples is burning charcoal in a barbecue. Once again, we see the disappearance of something. We see the disappearance of the charcoal. The charcoal is, of course, carbon. But there are other things going on. Most obviously, the production of heat energy. As we shall see later on, this is an exothermic, a heat-delivering reaction. Furthermore, if we were to trap the products of the burning of charcoal in a barbecue, they would not be carbon. They would in fact be carbon dioxide. An invisible change is also going on in this process. Oxygen from the air is being consumed, and together both carbon from the charcoal and oxygen from the air are combining to give a new compound. So this gives, with oxygen in the air, carbon dioxide. This is a new compound. And consequently, this too is a chemical change. Our final example in this problem is the preparation of cream from whole milk. Now, you may not know very much about this process, so let me tell you just a little bit about it. You take whole milk and effectively you centrifuge it. You allow it to settle into different phases under a gravitational field. In the old-fashioned way, you just let the milk stand and the cream would settle to the top, because cream, being the fat part of milk, is less dense than the aqueous part of milk. But in modern cream-making plants, they actually put the milk in a centrifuge and spin it at high speed to separate the cream. But there's no reaction involved here. Milk, in its original state, contains fat globules in an aqueous suspension, a watery suspension. And all we're doing in making cream is to take those fat globules and let them agglomerate to cream. And if we like, we can take the cream, mix it with the residue, the aqueous suspension medium of the milk, and homogenize them and get milk back again. So this is reversible. So all these indications show that this is just a physical change. So once again, to emphasize, chemical changes involve the formation of new compounds or the destruction of old compounds, usually both. Physical changes involve changes of state from one phase, gas, liquid, or solid, to another, or vice versa, or separation of different phases, one from another. In this case, fat from an aqueous suspension in milk-giving cream. This example asks what evidence we would try and accumulate to show that water is a compound rather than an element. And let me give you just a little bit of chemical history. For centuries, millennia even, water was believed to be one of the essential elements making up all of the stuff on Earth. You may have heard of this theory. It originated around the time of Aristotle and the ancient Greek philosophers, and it suggested that all material was made up of earth, air, fire, and water as the elements. Nowadays we have a very different view of elements. Elements, in our view, are the simplest materials into which things can be resolved and from which compounds can be constructed. And so there are two ways in which we can show that something is a compound rather than an element. The first of these is analysis. The separation of a compound into its elements. And water can be relatively easily separated into its elements using the following very simple experiment. We take a little water, and we put in two electrodes that we connect to a battery, an electric battery. And very soon we see bubbles accumulating at each of these electrodes. Those bubbles turn out to be hydrogen gas at the electrode connected to the negative pole of the battery, and oxygen gas at the electrode connected to the positive pole of the battery. We have analyzed water, separated it into its elements by means of electrolysis, that is, breaking down by an electric current. Later on in the course, we will be discussing this phenomenon of electrolysis in some detail. In this particular example, we have taken liquid water and broken it down by electrolysis into its constituent elements. Nothing, by the way, that we can do chemically to either hydrogen or oxygen will make them simpler. That's why they are called elements. There are also more fundamental, more theoretical reasons, which again we will get into later in the course. So this is an analysis of water which shows that water is compound and not elemental. Now, the second approach to this problem is to explore synthesis. Synthesis is the reverse of analysis. It's the formation of a compound from its elements. Again, let us consider a simple experiment. We have a bulb in which we place a mixture of 2 volumes of hydrogen gas, which we know to be an element, and 1 volume of oxygen gas. We know oxygen to be an element also. And we have this bulb with 2 conducting wires, copper wires perhaps, sealed into it, and we connect these to a battery, a source of voltage. A little spark passes and we get a mild explosion, or it might be a large explosion depending on the amounts we have. And when we re-examine that bulb after the spark, there is not a trace of hydrogen or oxygen left. But we see drops of water. We can test it and make sure it is water. Drops of water formed on the inside of the bulb. We have synthesized water from its elements. It's the reverse of the equation above. And so by 2 quite separate methods, which are very general methods, analysis, breaking things down into their component parts, synthesis, making compounds up from their component elements, by these 2 methods we have shown that water is compound and not an element, thus overthrowing a theory that held the stage of science for 2,000 years.